It's another chill math stream. Let's find out what's going on. Hello, Herb. Oh, so quick on the chat. I've been live 10 seconds. Oh, so fast. Very regular stream schedule. This is the key for Twitch, if anybody's wondering. If you would like this kind of bang on 2 p.m. every single Sunday. Hi, Matt and Ash. It might not be the best content, but we can do the timings. There's a tagline in there somewhere, right? Might not be the best content, but it is regular. Ooh. Not the most frequent, just regular. People often mix those up. Okay, right. My plan for today, periodic functions, has a well-defined interval between things. That's how I like to roll. My plan for today is just to do more number theory. I was enjoying it last week, and it's the sort of thing that is bouncing around in my head in between. I realised, by the way, that we can now prove that there are infinitely many primes of the form 1 mod 4. I think it's the sort of thing where I've probably come across a proof before, but now we've got enough maths to do it. Hi, Thrice Shy. Welcome to the stream. Good to have you with us. I think I've set everything up. All my tech is suspiciously quiet, like it's just bumbling along. Sometimes all the fans go. Maybe that's waiting for me. Oh, and if you hear any beeping noises in the background, then congratulations, you've got better hearing than me. If you hear a beeping noise, let me know. It means that the dishwasher's finished or something like that. I won't notice because hearing loss. I'm in my 30s, but it's possible that it's possible I accidentally broadcast my dishwasher noise to the internet this afternoon. Timings. Hi, Mary. Right, okay. This is going to be a little bit chill maths to relax and study to. I noticed, by the way, that Cat Does Maths on Twitch is back. If you're not already following Cat Does Maths, you might like Cat Does Maths. Let me put a link to Cat Does Maths in chat. I don't know if they're live now. It'd be great if they were live now. We could do a sort of stream thing. I'll put a link in Twitch. There we go. So Cat Does Maths does the kind of, in some sense, chill stream, but done properly, where it's actually chill and people get some work done. One of the things on Cat's stream that I like is a box where, I don't know how this works, but a box where viewers can submit what they're up to, like what task they're trying to get done, and then everyone just quietly gets their tasks done, and then they report back. It's like this if we were all... It's like with a to-do list, seems like. Let's take that. Right, okay. So if you'd like a suggestion of a different Twitch stream that you could be watching instead of this one, Cat Does Maths. Yeah, do let me know if you hear beeping noises. It means that one of the machines. I think the dishwasher is going to win. They're having a bit of a race. Depends which thing wants to beep at me first. Okay. Primes to form 1 mod 4. Here you go, there's your task. Good. Primes to the form 1 mod 4. Primes that are 1 more than a multiple of 4. Where am I going to write this? I think over here, which is a bit daft, but whatever. We'll just wander over here. Good, that's a bit of space. So we've been looking at whether or not is a number A equal to x squared mod p for some x. So we've got a prime p, and we've got some number a. So this is some number. We've been asking questions like this. This is like the quadratic residue question, I guess. If that does exist, then we say that A is a quadratic residue. It's the residue, what's left over when you take some square and divide it by p and look at the remainder. Residue in the division sense, quadratic in the sense that you squared something. Okay, what's left over when you divide it by p? And if I turn this around a little bit, this includes the kind of interesting question, is -1 equal to x squared? Okay, mod p, and these should be equivalent signs, shouldn't they? For some x. Which is then fun because it looks like the square root of -1, right? Is -1 the square of something? Okay, mod p algebra. So I suppose this is going to demonstrate how modular arithmetic is kind of totally different from real numbers. For example, e.g., -1 is equivalent to 2 squared mod 5. So if p is 5, then yes. So the square root of -1 mod 5 is kind of 2, or -2. And those are different things. So it's kind of a fun game. We get to kind of invent square roots of -1. Mod p, we did some maths last time to prove that if there are square roots of -1, there's at most 2 of them, because that's a quadratic, and mod p respects quadratics and number of roots of quadratics. We did some maths last time for that. And we have done at some point on this stream a bunch of theory to let us know when this happens. Here's the theory. So suppose x squared is -1 mod p. My plan here is to try to recap some of the theory that we've done before, but in quite a specific case. I think it helps me understand it, to focus in a little bit, and it maybe helps us understand what we're doing to look at a particular case. There's another thing that we know. We know that x to the p minus 1 would be equivalent to 1 mod p. That's called Fermat's Little theorem. It says that any number you take to the power of p minus 1, you get 1 mod p. So let's say, suppose p is an odd prime. Most of them are. 2's a bit different, but whatever. Suppose p is an odd prime, then p minus 1 is even. So we have this thing, x to the p minus 1 over 2 is either 1 or -1 mod p. Those are the things that square up to give us 1. So x to the p minus 1 over 2, because x to the p minus 1 over 2 squared is x to the p minus 1. We just said that that's 1 mod p. So we've got thing squared is 1 mod p, which has got solutions 1 and -1. Again, there's a quadratic in there, a nice sensible one, x squared equals 1 with 2 solutions, mod p. So that's very nice. Okay, where am I going with this? So we did some theory that says this is how you tell, right? This is how you tell whether the thing is a quadratic residue or not. No, it's not. This is the thing you tell. This is the thing. Oh, what am I doing? Right, okay, so I've kind of got cases. I should probably have introduced my cases at the top. I feel bad about ruling out 2 halfway through. It feels rude to 2 that the number 2 might think it's being included and then it gets ruled out halfway. So probably I should put the conditions at the top. So if p is 1 more than a multiple of 4, maybe not so, just if p is 1 more than a multiple of 4. If p is 1 more than a multiple of 4, then this p minus 1 over 2 thing is even. Then p minus 1 over 2 is even. And that's relevant because my plan here is to write this x squared the p minus 1 over 2. Here we go, this is the good bit, there we go. X to the p minus 1 over 2 squared is the same thing as x squared to the p minus 1 over 2. And this first thing here, well, these are both x to the p minus 1, which is 1 mod p. But this x squared is supposed to be minus 1 mod p. I'm going to change my mind in a second. I'm going to change my mind quite seriously. This is good working out. Okay, this is going to be, I think, yeah, okay. I'm going to change my mind here. I'm going to do the other case. So I'm going to change this to if p is 3 more than a multiple of 4, then p minus 1 over 2 is odd. Right, okay. And I think this is in the lecture notes somewhere, but who knows? It's fun to sort of explore it this way around. If p is 3 more than a multiple of 4, then p minus 1 over 2 is an odd number, because you subtract 1, you get something that's 2 more than a multiple of 4. Then you divide it by 2, so it goes from 4k plus 2 down to 2k plus 1, an odd number. Okay, which means that it was important because I've got minus 1 over here to the power of p minus 1 over 2, which is why I'm playing with the even odd cases for whether or not this power is even or odd. I'm trying to think about that, which, if I backtrack a little bit, is thinking about whether p is 3 or 1 more than a multiple of 4. Anyway, this would be minus 1 if I do this thing. Minus 1 to an odd power. And this is a bit, oh no. So we have this thing, we have this quantity that's equal to 1 because of Fermat's Little theorem. And then mess around with the powers a little bit, and you say, well, x squared was supposed to be minus 1. So, and then that's to an odd power, so that should be minus 1. So this is, oh no. This is a contradiction. So it says that if your prime is 3 more than a multiple of 4, then you cannot have a square root of minus 1. And I think the fun thing we've found out in this course is that because minus 1 to the p minus 1 over 2 is equal to 1 mod p, if p is 1 more than a multiple of 4, well, this problem doesn't happen if p is 1 more than a multiple of 4. That's not really enough, but there's some stuff we've done in the course to say how many quadratic residues there are. Around in lecture 2 or 3 or something. We thought this is actually sufficient. This bit over here shows that it's necessary in order to not have this 1 equals minus 1 contradiction. But in fact, it's sufficient. In fact, that's sufficient. And the course has this nice claim, this number theory course that we're looking at, has this kind of nice claim that there is such an x with x squared equivalent to minus 1 mod p. Which is kind of nice, but a little bit abstract, right? There is an x such that x squared is minus 1 mod p, if p is 1 more than a multiple of 4. So primes like 5 and 17. I think this is kind of mysterious and cool. Let's try and look for them. So if p equals 5, then the square root of 1 is, we saw this one is 2 squared is minus 1 mod 5. If p is, well, that's the next one. I'm looking for things that are 1 more than a multiple of 4. So I go up to from 5 to 9, that's not prime. Then I go to 1 more than a multiple 13. Now, goodness me, what am I going to put in here? What's 1? So I want 1 less than a multiple of p. A square that's 1 less than a multiple of p. And that's quite hard to think of. So look for n such that n squared plus 1 is a multiple of 13. And the course tells us that we're going to find such a thing, but it's not obvious to me, right, where we would find it. Maybe there's a pattern. I would quite like to explore that pattern, I think, if there is one. The proof's kind of non-constructive. The proof is that this thing there is such an n or such an x, But it's not enough to actually find one. So in this case, it's 5. If you're playing along at home, 5 squared is 1 less than a multiple of 13. So that's nice. I mean, it tells you that 5 squared, 25 is 1 less than a multiple of 13. The next thing that's 1 more than a multiple of 4 is 17. So now we're looking for n such that n squared plus 1 is a multiple of 17. And I haven't really thought about this before, so maybe this is easy. Oh yeah, look, 4. 4 is nice. 4 squared is minus 1 mod 17. So far these are all quite small numbers. Maybe that'll keep going, maybe that'll stop. The next prime is, the next one of this format is 29, because 21's not prime, 25's not prime, but 29 is prime. So what, n squared plus 1 multiple of 29? And now I'm not sure I can think of this. Over to chat, I think. Hi Twitch chat. We're exploring a little bit of theory from number theory, circular. The idea is that if your prime is 1 more than a multiple of 4, then you can find a number such that n squared plus 1 is a multiple of that. Oh, 12? No, wait. Now I've got to think. No, you're making me do maths. Right, so I want to add one. And you're claiming that's a multiple of 29? Doesn't look like oh, it was a multiple of 29. That's nuts. That looks nothing like a multiple of 29. Thank you, chat. 12 squared is minus 1 mod 29. Okay, so I guess, have we invented a good game? Is this actually hard? Welcome to chat, Calon293. Herbs in there too. Until I hit divide by 29, that really somehow threw me. It did not look like a multiple of 29 at all. Should we do the next one? Because I haven't seen a pattern yet. Maybe there's no pattern? 2, 5, 4, 12. It'd be nice if there's some formula in terms of P, right? So I'm trying to think of anything, right? These are all 1 more than a multiple of 4. So you can do some tricks. Like P minus 1 divided by 4 will always be a thing. So I'm sort of looking out for whether... Are these all slightly smaller than half? No, they're not. Okay. 33. 37 is the next one up. 8 more, isn't it? And that is prime. So n squared plus 1, is that ever a multiple of 37? I mean, we know it is, but can we find something where n squared plus 1 is a multiple of 37? It looks like we're going to have to go, well, n is going to have to be, at least 6, right? At least 6, because of the size of n squared. And in fact, 6 squared works, doesn't it? Because 6 squared is 36, which is 1 less. It's slightly annoying. That means that any pattern I was going to have. Wait, what's 16? What's 16 doing? No, surely not. Surely not another one. Oh, hang on. Okay. Let's do one more. So one way to do this is just to square everything and see what you get. You only have to square up to 20 squared or something before you inevitably hit something. Because squaring the numbers from 20 up to 41, from about halfway upwards, it's like squaring the negative numbers. Modular arithmetic's great. So this search looks quite hard? I don't know. Factorising numbers is tough. Am I being silly? Is it something like... Yeah. Actually finding the quadratic residues. 9. I trust you a lot now. 9, yeah, thanks. First time in chat 10 minutes ago. Welcome to the stream. That's a good shout. Okay. Something you can do, by the way, is to use this to generate new primes 114. I mentioned at the top of the show that you can turn this to proof there's infinitely many primes that are one more than a multiple of 4, like this. These ones. First, I think we need to agree that the factors of n squared plus 1 are, well, maybe 2, maybe the number 2, primes that are 1 mod 4, primes that are 1 mod 4. You can't have any primes that are 3 mod 4 in there, otherwise that n, that value of n squared plus 1, would be an example of a square root of minus 1 for that prime that's 3 mod 4. That's the converse fact again. Oh no, that's the direct fact that we mentioned above. Oh no, just off the top of the screen here. That that if your prime is 3 more than a multiple of 4, then you can't have x squared plus 1 being a multiple of that prime. Which, flipping it around, says, well, if x squared plus 1 is a multiple of some prime p, then it's not going to be one of these ones. Otherwise, x squared will be minus 1 mod that prime. So that means that n squared plus 1 has only got one sort of odd prime in its prime factors. I find this quite hard to believe. I had to go and, when I saw this, I had to go and factorize some numbers, right? We've been doing it one way around, where I give you a target prime and you find me a square. But actually, the other way around says that when you look at these squares, n squared plus 1, you'll only find primes of this form. So if I take, I don't know, some nice prime sort of thing. Yeah, so 13 squared plus 1. N doesn't have to be prime, actually. N doesn't have to be prime, it's always true, but we'll do a couple. That's 170, which is 2 times 5 times 17. And 5 and 17 are both examples of primes that are 1 mod 4. Yeah, maybe that's a coincidence. 14 squared plus 1, which is 197. Which might be prime itself, actually, now that I think about it. Yeah, cool, that's prime. Ooh. I don't know where we've gone. Where have my notes gone? What did I do? I was trying to circle. I just went over the page and everywhere. Okay. 197 is prime. There we go. 15 squared plus 1. Let's just try a few more. These are like nice large numbers. Wow, talking fail. 2 times is 113 prime. I've got a separate tab open because I don't know my primes. Yeah, 2 times 113. So that's prime. You can use this to generate new prime numbers of the right format. If you look at 4 times, and then let's take all the numbers and square that, all the numbers up to k, square that and add 1. Then this is a huge number of the form n squared plus 1. Well, I guess n is like 2 times 3, yep. It's like k factorial or something. But its prime factors must be larger than k. Because this chunk here with the square on it is definitely a multiple of anything you name up to k, and I've got a plus 1 on the end. So like that classic proof of primes. Classic proof of the infinitude of primes. So that means the prime factors must be larger than k, which means that for all k there exists a prime such that p is prime P is 1 mod 4, and P is greater than K, which is a statement that there are infinitely many of these things. You can keep increasing K. Okay, this is a rather tidy proof. Oh, I found out, by the way, this version, for the there are infinitely many regular primes. I saw a second version of it where, well, so the classic proof there are infinitely many primes says, suppose there are finitely many primes, list them, multiply them all together, and add 1. But I saw a slightly better proof, I think, or slightly faster proof in a way, that doesn't bother listing the primes. It just says, or choose K, multiply all the numbers together up to K, and add 1. And then that's not a multiple of anything up to K, so it's prime factors that are larger than K. So for all K, there's a prime factor that's larger than K, prime number that's greater than K. You don't have to bother listing them, which is odd. I've always thought of that as a sort of classic proof by contradiction, whereas this feels a lot more direct to just say, I don't care about your list, right? But throw in all the other kitchen sink stuff as well, like the number 4 in here. It's not really doing anything, it just avoids. So it means I don't have to think too much along the way. Makes the number bigger, but it's already huge anyway. It is nice that Google knows whether things are prime or not. I trust it entirely on that matter. Right, okay. I would like to have a quick look back at the proof that beeping noise. I'm going to take a very quick ad break for me to stop the beeping noise. I did hear the beeping noise. I knew it would happen. Right, cool. I'm going to run an ad. After a quick ad break, we're going to look back at the proof and then try and learn some new number theory. We've got infinitely many primes to the form 1 mod 4. I think that's nice. Yeah. Right, good. Okay, back in 1 minute 30, so I can stop that beeping. One of those days. Maria got no ads this time. Lucky you. I don't really know what happens if you get no ads. I guess you get to look at the Be Right Back screen for a minute and a half while I deal with a machine. Right, good. I think it means we have no pre-roll ads for 29 minutes. So I don't know what that means really, but if you've just joined the stream and you didn't have to see a pre-roll ads, then hooray, we did it. If you haven't been before, ads help support charity in the sense that any money that I get as a result of ads is given to charity in advance. I'm a bit worried that Twitch will never add up enough. It'll never converge to a number large enough that they'll let me extract it. So I have pre-donated. Has the sky been blue and pink? It was kind of purple at one point, in quite an ominous way, a couple of days ago. It's very cloudy at the moment. I'm looking outside now. It was weird. Are we having another one of those times when the sky goes weird? We had this, didn't we? Was it 2020 when the sky was just weirdly orange all the time? For some reason? Sahara dust, maybe? I think this was a thing. Am I making this up? Maybe not. I can't find the bit of the notes where we demonstrated that there are exactly that many of them. But it's going to come up, isn't it? Here it is. Exactly p minus 1 over 2 quadratic residues. We must have looked at this. Or maybe we looked at it in a different set of lecture notes at some point. Okay, right. I think we're going to skip lecture 5, which we did look at in a bit of despair last time. It says that groups like this are cyclic. This is the group of units. Mod p to the j. Not in a PJ mood. And apparently 2 is weird. So if this comes up again, looking for primitive roots, then I'll remember to come back to lecture 5. Right. But my plan is maybe to look at this. Yeah, okay. I think I've got my sequencing all wrong because now we're going to learn about quadratic residues, the thing that we foreshadowed earlier in the stream. Okay. Right, we're going to start with n equals p prime. I like this because I also sort of care about whether there's like x squared is 1, x squared is minus 1 mod n in general, like how 3 squared is minus 1 mod 10. I think this is a sign that mod 10 is a good kind of system, that we have a square root of minus 1 in mod 10 world. I just think that's a good idea. Oh, we've got 2 actually, haven't we? Because 7 squared is also minus 1 mod 10. Those are plus and minus 3, but you know, all very nice. Good. Okay. Other numbers are available because of the nature of modular arithmetic, right? Like 13 squared is also, you know, we're not going to play this. I'm going to play this game right now. Okay. This idea about plus or minus 3, so 7 is like minus 3 in the mod 10 world. This idea is going to be what's happening here, right? P being an odd prime, then they're exactly p minus 1 over 2. Right, we're supposed to read the notes, so let's have a quick skim through the notes. If the solution called a quadratic residue, otherwise quadratic non-residue, 1 is always a quadratic residue because 1 squared is equal to 1. Welcome to chill maths. 2 is a quadratic residue mod 7. Good. But 2 is a quadratic non-residue mod 5 because mod 5, 1 and minus 1 squared to 1 and 2 and minus 2 squared to 4 mod 5. Sorry, I thought about that for ages. Oh, minus 1. They're too busy being the square root of minus 1 to help give you the square root of 2. Not great. How many quadratic residues are there modulo prime? And it's kind of half of them because they pair up. Minus a squared and a squared give you the same thing. And there aren't any duplicates because of solving equations. Because P is prime, and the thing I love about Vicky Neal and the lecture notes is that they have these kind of comments. P is prime, we're using this so that when you see this equation, you know that one bracket or the other is 0. That happens when P is a prime because this equation reads P divides and then 2 things that I can call A and B. And if that's true, then P divides A or P divides B, which is not true if P is not prime in general, right? Because you've got things like 2 times 5 is 0 mod 10. This is a weakness of the mod 10 system, that you have non-trivial things you can multiply to get 0. In a way, we have a stronger system. Good. Okay. If 10 were prime. If only 10 were prime. Be good things and bad things. Anyway. Okay. I'm messing around. So there are 2. The map of squaring is 2 to 1. Okay, it's proof 2. Oh, using primitive roots, for which I is due to the I quadratic residue. Oh, so this is going to look at okay. Oh, the groups. If the group is cyclic, yeah, the group is cyclic. No, wait, is this true? What am I talking about? I'm going to read it. Stop talking, start reading. Yeah. P-adic numbers are in a recent Oxford Maths video. We make these videos of different mathematicians explaining their maths or talking about their maths. Somebody's had a go at p-adic numbers recently. I haven't watched it. I should probably watch it. I say we in a kind of general sense, like at work. Right, okay. If I is even, then g to the I is a quadratic residue. But these are the only ones, and then we're going to do a little bit of proof that these are the only ones, right? Where I is even, every other one. Suppose g to the I is x squared, then x is g to the k, because of course it is the group cyclic. So this is cyclic group. So g to the I is g to the 2k. This does not imply that I equals 2k. Why not? Why not? Hang on, let me mess around. Yeah, it's this, right? Still looks like I is equal to 2k. Oh, it could be plus a multiple of p? There's lots of powers of g. They give you 1. If we know the order of g in the group, g has order p minus 1. Oh, so p minus 1 divides I minus 2k. So I was saying mod p, but I should have been saying mod p minus 1. It's kind of close. Okay, p minus 1 is even, so 2 divides that, so 2 divides I. Application of quadratic residues. Is it an application? Okay. P minus 1 is even. So 2 divides that. Why on earth is it called G? So in group theory, you've got big G for your group, of course, and then you tend to have little g for an element of the group. This is a little bit like how, in set theory, people usually try to use capital letters for sets and lowercase letters for elements of those sets. Maybe with the pairing that A lives in A, B lives in B. It doesn't have to be like that, of course, but you might choose to set it up like that. So people quite often, if they need a random element from a group, or just to remind you this is in a group, I call it G. This is quite an important. The thing about primitive roots is quite an important thing about the group. It says that the group is generated by some element G. I guess that's a separate reason. It's a group generator. It's a group element, and it's also, in this case, group generator. I don't actually know if people are pick G because G is the first letter of generator, or because it's the first letter of group. I don't know. I haven't really thought about that before. But earlier on in the bit of the course notes that we kind of skipped, we looked at the elements of the group being g to the 0, g to the 1, g squared, g cubed. This idea that g generates the group up to g to the, I guess I've put g to the 0 in, so I should say g to the p minus 2. Feels weird. Good question. It doesn't feel very prime numbery to call something g. It doesn't feel very natural numbers. Like maybe we should call it n or a. Those feel like nice solid whole numbers to me. Up here, x and y, they make me feel like real numbers. This is silly because they're just letters of the alphabet. Let it go. That was advice to me. Good. Okay. Good, we got some quadratic residues. Oh, so this gives us a way to know if things are quadratic residues. You take your group generator and raise it to even powers. And those are quadratic residues because for the square root you take it to half as much power, and that's enough of them. Yeah, I quite like this proof, this bit of the proof. It's forcing us to think about division and orders of things in groups. I feel like I would have liked is that enough of them? No, I suppose I prefer the first proof. That's what I'm saying, we should switch to the second proof once we've worked out what they are. I think I skipped 2 pages there. Oh, are we good? Maybe not. Maybe I didn't skip 2 pages. Page 11, page 13, page 12. What is going on? What is going on? Page 11, page 12. I'm very confused. I'll just keep going. Okay, so we've got some bullet points here. If you've got 2 quadratic residues, you can multiply them together to get another one, because if A and B are both quadratic residues, squares of x squared and squares of x and y, then AB is the square of xy. If you've got non-residues, then suppose that A and AB were both quadratic residues. Group theory is great, you could rearrange that to get, can I see that happen? B would be, this one divided by that one is a square as well. Good. That looks horrible, but is just some number, mod p. Mod p is lovely, you have inverses of your elements. You can undo multiplication. And then quadratic non-residue times quadratic non-residue is quadratic residue. That's a bit more surprising, right? But I suppose, yeah. Hello, Fourier analyst. Yeah, cubic reciprocity. I don't know, man. I've got to learn the quadratic one first. Give me a chance. Before I get into Roger Heath Brown's proof for the infinitely primes of the form x cubed is 2y cubed. This is a fun troll. I like this. This is high effort. Is the username? Did you do this specifically, or do you go around other maths people as Fourier analyst? Yeah. I should remember it from fluid dynamics. You're right. Good. Here's the Legendre symbol. Anyway, I don't love the way it looks like a fraction, and it looks like a binomial coefficient, and it looks like a vector, and it looks like brackets around a fraction. What are you gonna do? So this behaviour at the top, 1 minus 1. I didn't really engage with this, I suppose. This one here feels like there's not enough stuff left over. So you've got your quadratic residues, and you've got your quadratic non-residues. So this is mod p, I think. This is all mod p. Feels like there's not enough stuff left over. If you do a big multiplication table of your quadratic residues and your quadratic non-residues, then in your big multiplication table up here, we've decided you will definitely get loads of quadratic residues. Over here, you'll definitely get loads of quadratic non-residues. And then I suppose this is a Cayley table. It's got every element in every row and every element in every column, like a Sudoku. So this must be more quadratic residues down here. That's where they must all be hiding. They can't be up here. They get pushed down over here. And they can't be over here. They must be pushed over that way. Yeah, the map in each column, you could say, the first bit of that argument's enough. In each column, you could say, multiplying by a particular quadratic non-residue, choose your favourite, is a 1-to-1 permutation of the group elements. So if it's mapping quadratic residues to quadratic non-residues, then all the quadratic non-residues have to match to quadratic residues, there's nothing else left. those sets are equal in size, being relevant somewhere in that argument. Okay. Oh, there it is. There it is. Here are the examples of 2 and 3 and 2 and 7. And here's Euler's criterion, the thing that we wanted. Whether or not something is a quadratic residue. And here it goes. Right, this is what we were looking for. By Fermat's little theorem, this is true, so this is true. So anything of that form, no way, don't get ahead of myself. By the first proof we saw, if x squared is 1 mod b, then x is plus or minus 1. So here it is. Quadratics are so nice, mod p. Let G be a primitive root mod p, and so that A is due to the I. A is generated by G, some generator. If I is even, then we're good. That gives us p minus 1 over 2 solutions, so we're done. Those are all the solutions. It's Lagrange's theorem, the number of roots of a polynomial is at most the degree of the polynomial in the mod p world. Okay, so this is good enough. And we know that that's linked to being quadratic residue from before. Okay, so I like the way Vicky's, I guess, you do 2 proofs and then you use 2 proofs along the way. Good, okay. I think this is fine. If you're happy that a to the p minus 1 over 2 is 1 half the time and minus 1 half the time, and once you've spotted that if it's 1, then a to the, oh gosh, if it's minus 1, then a cannot be a quadratic residue because a would itself be something squared. So this would be something to the p minus 1, which would have to be 1. So once you're happy that if this object on the left is minus 1, a cannot be a quadratic residue, then there's kind of not enough space left over for all your quadratic residues, mod p. Good. Totally multiplicative. If p is prime and ab are integers, then this, oh my goodness, consequence is a group homomorphism. I wasn't paying attention to the chi thing above. Where's chi? Oh, from z mod pz onto 1 and minus 1, going to this group homomorphism. Because it respects multiplication. Right, good. Okay. Okay. Anything that maps to 1 times anything that maps to minus 1, great news, you're going to get something that maps to minus 1. Homomorphism means that phi of what's on the left, phi of A, I guess it takes numbers in P mod P, phi of B is phi of AB. It kind of respects multiplication. And that's what this is. Chi is set up to be this quadratic residue Legendre symbol thing. I guess we introduced chi just before we knew that was the formula for it. Right? We said chi. Oh no, just after we knew the formula for it. It's a sensible way around. Work out the formula and then look at that thing. Oh, and I'm supposed to check 2 separately. What's going on there? P being an odd prime. Why do we need it? Oh, we needed p minus 1 to be odd. No, we needed p minus 1 to be even. So we're looking at odd primes. It seems a congruent mod p by Euler's criterion. Wait, what's going on? I think I'm mixing up Euler's. I've got to remember. Right, okay, so when we see Euler's criterion, we've got to somehow remember this, which says that you just take the power of p minus 1 over 2. You've got to remember that, get some intuition for trying that sometimes, and also remember it's named after Euler. That's a lot to take in. So this thing, the power of p minus 1 over 2, is this step here, whoop, and also this one and this one are all Euler's criterion. 3 times, and then checking the multiplication in the middle. These things are congruent, not equal. What's going on there? Does Euler's criterion have a congruence in it? Right, okay. Because if the p minus 1 over 2 could be just anything, could be huge. And we've used it twice. But in fact, these things are equal, right? Yeah, actually equal. Yeah, because they're not very large, so we're okay. Right. This is a weird proof. It sort of says these things are 1, 0, minus 1. Mod p. When you multiply them, let's use these formulas, which introduce huge multiples of p, but multiply nicely. And now, okay, up to that huge multiple of p, it's this thing. So we might have gained some multiples of p along the way, but definitely not, because actually they were secretly just numbers 1, minus 1, and 0. That's really odd. I'm not sure I've seen something like this before, where you prove a congruence and then limit it down to equality. Normally once I've seen congruences, it means, well, we're just going to not know until all the way through. We're going to have this thing be congruent all the way through, like in Euler's criterion. The thing just ends up saying mod p at the end. This thing's actually equal. Here's a third proof of lemma 19. Lemma 19 being that there are p minus 1 over 2 of these things. Because group homomorphism-y sort of stuff, maybe? Here we go. Add them. Add them together. Right, okay. Oh, right. If they balance out, they're going to balance out, so they'll be equal in number. This is nice. And this, because B just permutes the elements. Okay. Right, this is the group theory idea of multiplying by B, just permuting all the elements. If you're going to sum. These things are, differing by kp or upstairs doesn't matter. So this really is equality, not the thing inside the symbol is changing. Maybe mod p. Is this in some order mod p, right? But then it doesn't matter. I have my own notes. That thing is minus 1, is it? Is this of multiplying through looking at a quadratic non-residue? Okay. So this thing is 0. Why did we do that? Why not pick a quadratic? Oh, we don't know there are any, I suppose. No. I want to look back at the beginning of proof 1 of lemma 19, which was, oh gosh, only 2 pages away. There are at most p minus 1 over 2, so you can find something because the squares pair. The squares pair. Pairy squarey. Good. Okay. Here we go then. Here's the thing I did at the top of the show. Minus 1 is a quadratic residue mod p if p is 1 mod 4, and it's not if it's 3 mod 4. Brill. There you go. Lovely. Okay. It's lecture 6. I think my aim is to get to end of lecture 8 maybe. Try and do four a show. 6 shows. Month and a half. That's a lot of content, isn't it? Let's have a look at this proof at the start of lecture 7. See if I can speed up. I'm probably going to slow down. When have I ever sped up during doing anything? Multiply them together. Oh, this is a proof that we saw in somebody else's lecture notes, right? Multiply everything by A and then cancel. Where does the sign come from? Well, it comes from where these things go to. So this is in grey. I think it might be non. Oh, it's like a note before we get to the thing. Here's some non-standard notation. Square brackets for pick the one that lies in here with minus signs. We're interested in all of these things up to that one. Good. Gauss's lemma. Yeah, right, okay. We saw a proof of this. We really struggled with it. There was about about 3 weeks ago, something like that on the show. I don't watch them back. New is the size of the set such that this thing gets mapped to a negative number. Compute them and count them. And this is fair enough, I guess. And here we go. Here's the layout. Consider these things. Count how many of them are negative. Could two be the same? No. Since no two of these things are congruent mod P, P would have to divide by the difference, and P can't divide the difference because the difference isn't big enough. Can two divide by a sign? No. Differ by a sign. Oh, this one is negative, that one. Because then you would add them and you get 0. But you can't because even the largest one, adding that to any of these doesn't get you far enough. Okay. So these are that in some order. You of them are negative. So this, so that, divide it, brill, get this. So this is a different expression which is equal to that, equal to this a to the p minus 1 over 2 thing, mod p, which is then equal to this thing, mod p. More importantly, because it's minus 1 or 1, that mod p thing goes away. And both come from this set, so this gives actual equality. The second time I've seen this, that we prove something mod p and then get actual equality. Mod p, actual equality. Okay. Oh no, right, okay. P squared minus 1 over 8. That's a nice formula. Okay, here we go. Is 2 a quadratic residue? Can you find me an x that squares to 2 mod p? And Gauss's lemma says that you should do this and count how many of them get mapped negative. Here they are, they've been doubled. How many of these things are kind of in the on the negative side of 0? I think the other lecture notes we looked at proved that you could do this for kind of any set, any interval I, which made things quite tricky. Like the interval I needs certain properties, which there's lots of choices that satisfy those properties. Cases, good. I find this quite hard to actually check, but fine. Okay, great. Different cases, sort of whether these things get mapped doubled past this or not. So what is this? P is 1 or 7 mod 8, plus or minus 1, plus or minus 3. Whether or not 2 is a quadratic residue. It is if P is 1 or 7. This formula on the right is quite funky. I'm not sure I'd have thought of this, as this is a shorthand for all the stuff in curly brackets, the case stuff. It's kind of cool, right? But p squared minus 1 might be 0 if p is plus or minus 1, or it might be 4 if p is plus or minus 3. 9 minus 1, no. What? 9 minus 1 is 8. Those are both. Wow. P squared minus 1. 0 and 4. No. What am I doing? If p is 1 more than a multiple of 8, then p squared is 1 more than a multiple of 8. Yeah. P squared minus 1 is a multiple of 8. Oh, but is it an even or an odd multiple of 8? This is mad. What? This is crazy. The conversion here is like really wow. because it's identifying, okay, I guess up here is p squared minus 1 a multiple of 16. P squared minus 1 is definitely a multiple of 8. That's already fun. Yeah, because any odd number squares to 1 mod 8. That's already amazing. So p squared minus 1 is definitely a multiple of 8, and then this question said, aha, but is it a multiple of 16? That's brill. So if p is 8k plus or minus 1, then when I square it, I get, oh my goodness, right, I get 64k squared, which is a multiple of 16. I get plus or minus 16k plus 1, so 1 more than a multiple of 16. But when I have 8k plus or minus 3, I get 64k squared, which is a multiple of 16, plus or minus 3 times 8 times 2. Wait, this is also going to be, oh no. Oh, I don't like this. What is this? Plus 9, which is 9 more than a multiple of 16. Rather than 1 more than a multiple of 16? Good, right, okay. So if I take off the 1, then I get, in this case, something that's a multiple of 16. And in this case, I get something which is 8 more than a multiple of 16. So divide that by 8, and you get something which is 0 or 1, and then do minus 1 to the power of that. That's amazing. What a technical challenge to construct a single power that captures all of those different cases. Kind of want to do something mad. Let's try something mad. So we have a sequence which goes 1, 3, 5, 7, and we want it to be 1 here and here. We want it to be minus 1 here and here. And my plan, and then I guess then this is going to repeat, right? It's going to repeat. 9, because 9 is 1 mod 8 as well. So my stupid plan is I reckon I can put a sine wave through those points to make an even more mad right hand side. Which still works, right? I think this is mad and cool. Squaring p, take 1, is that a multiple of 16? Wow. So I want to go doing something mad, which is going to be this. So I'm going to have turning points on my sine at 4 and 8. And I suppose it's got a turning point here at 0 as well, which actually makes me think it's more like a cosine. So what's the period there? Cosine 8. So let's go cos 4 pi p. Quick check. When p is... No, divide, right? So when p, maybe a pi in here as well. Yeah, this is looking good. When I put in p equals 4, not sensible, but I get this minimum here because this is cos pi, which is minus 1. And then when I put in 8, I'll get cos 2 pi, so I'll be back to where I started. Good. Okay, I need to scale this because this has not got the right value at 1. That'll be cos pi by 4. So I'm going to divide it by cos pi by 4. Wait, hang on, I probably know cos pi by 4 if I think really hard. Like root 2 or something? 1 over root 2? It's a chill Sunday math stream. I can't remember how radians work. That's 1 over root 2, isn't it? Cool, yeah, I'm going to use that, I think. I'm going to submit this as my equals root 2 cosine pi p over 4. We're playing the mad right hand side game. I can play too. Here's a cosine that does the same sort of thing. Yeah, great. I'm really pleased with myself. It's got the right periodicity, right? The key thing is whether is this mod 8 behavior. Mine does mod 8 behavior. So if I add 8, then it's multiple of 2 pi. My cosine will see that. And I think it's got the right values. Don't write in if it's got the wrong values. That's a 1. So put in 1, you get cos pi by 4 is 1 over root 2, you get 1. You put in 3, perfect, you get cos 3 pi by 4, which is minus 1 over root 2. Brilliant. And then it repeats on the way up again. 5 pi over 4 is low. Good, okay. You put in something that's not prime, ooh, not an odd prime, then bad stuff happens. That's one of the silliest things I've done on a live stream, I think. Here's the law of quadratic reciprocity, which is a real banger. One for the ages, I think. There's a relationship between, if you've got 2 primes around, P and Q, you can play this game. I've never really understood the proof of this. I've seen it several times, which is a terrible admission, right? That I've tried studying it, I've tried reading it. I think people have explained it to me multiple times. Never really got it. I'm going to have another go now. I'm on the high of writing down a stupid cosine. I'm going to have a go at learning a thing that I've never really been able to learn. It says there's some relationship. Some relationship between whether Q is a quadratic residue mod P and whether P is a quadratic residue mod Q, which just already hurts, right? I mostly care about whether -1 is a quadratic residue, and that's not an odd prime, so we don't get to flip. And I care a bit about whether 2 is a quadratic residue, but we just did that one. And that's not an odd prime. So the correct question is 3 a quadratic residue mod 5? Is 5 a quadratic residue mod 3? But those things are kind of related. According to, here's another -1 to the power of some weird stuff. Very tempting to write that in terms of cosines as well, but I know, quit while I'm ahead. Too much of a good thing. Homework for you to try at home. We're looking for a function here that switches between -1 and 1. That's some kind of predictable intervals, depending on whether P is 1 or 3 mod 4, and also whether Q is 1 or 3 mod 4. You've got to be able to do something with that, right? I mean, the product of 2 things. You've got to be able to do something with that. Not me trying to tempt chat into writing down stupid cosine rules for number theory. Okay. What is going on with these minus signs? P, if they're both 3 mod 4, but as soon as you've got one of them, including if they're both, it feels like it should switch back, right? Let me have a quick think. If they're both... Yeah, this looks wrong. If they're both 3 mod 4, then P minus 1 over 2 is odd, because they are primes like 3. They're primes like 3. 3 minus 1 over 2 is 1, which is odd. So that'll be -1 to odd powers. Oh, no, hang on. Oh, chat, I hadn't... Bad news for our cosine rule, right? This isn't the product. I was imagining this to be -1 to the P minus 1 over 2, -1 to the Q minus 1 over 2, but that's not what it is, because that would be adding the powers. I should go back to A level. It's not that. It's something harder to calculate with the products up here. Ooh, and here's a challenge to do with cosines. A challenge we should try our best to avoid doing. Okay. So now I can see that I should focus on this number up here. Are these separate terms odd or even? And now I can kind of see that if one of them is even, you get an even thing. If both of them are even, or even more even, it's only if they're both odd that you escape. To get this odd power, to get an actual -1. Okay. If P is equal to Q, then you're not a quadratic residue. right? Even though 0 squared is 0, because we're just banning you from the mod p world, right? We're looking at units. We want things to be co-prime. Anyway, if they're distinct odd primes, then you can do this. Which, this would be false. So somehow this would be false. Right, this would be false if they're equal, because these things would both be 0 on the left, and that's not 0. What's going on there then? Oh, people are multiplying through. Yeah, okay, or kind of dividing by this thing. Which is either 1 or -1. And then dividing is like multiplying both sides by it. Which is kind of weird. Okay. Multiplying both sides by 1. It's a weird trick that is surprisingly good. Oh, here are some examples. Maybe this does look good. Maybe this is good. Is 19 a quadratic residue mod 73? You flip it, and then you take the kind of remainder. And 16 really is a quadratic residue, so we're good. So 19 is a quadratic residue mod 73. It is quite appealing. So you can flip it when you have primes. You can't flip this one because 16 and 9 are not both odd primes. So we've got a game here. You do multiplicity sort of stuff. So like 219 to the power of 4, and then you could flip it. Oh, and 219 is, yeah, like 219. I think I'm just going to pronounce it by saying the two numbers. Is either is or isn't. Not quite prime. And then it's the power of 4. 2, 4, 8, 16. Yeah, brilliant. Okay. This is a different way of saying it. Obviously, is a square, but hey. Okay, we've got a little game. Okay, you can flip them upside down if they're both odd primes. You can do this remainder trick, and you can do this multiplicativity trick. And oh no, there's a 97 squared minus 1 over 8. Don't love that. Using 2 over b and LQR, law of quadratic reciprocity. Okay, LQR. So we've got to remember this statement, probably this equivalent statement, maybe this third statement with its different cases. We've got to have some sort of intuition for all three of them, and we've got to remember that it might be called law of quadratic reciprocity or LQR. So it's going to be quite hard to try and internalize all of this. Good, right, down we go. Is 34 a quadratic residue mod 97? Wow, we can use multiplicity. And then that's a 2. We know about 2. We've got a special rule for that. I worry here that somebody's actually calculated this. That 97 is... So the formula is a way to kind of... I'm going to use my cosine at this point. Not that that would be better. But I think you're supposed to look at 97 and say that 97, gosh, is one more than a multiple of 8. So it's in that first case, plus or minus 1. So you write 1 here. And you've got this leftover bit, 17, 97. And they flipped it, remaindered it. Oh, flipping it and taking the remainders feels like the zoo. Feels like the Euclid's algorithm, right? These things are getting smaller and this algorithm will terminate. Something like that. You can only flip it when you get a prime though. So you might have to expand. You expand it into smaller numbers. So we're making progress. This feels like an algorithm. Any computer scientists in chat? Does this feel like an algorithm to you? Thresher agrees. It's an algorithm. The numbers are definitely getting smaller. And I think all of the tricks we're using reduce the numbers. Or flip it over so we've got a big thing on the top and we can keep using tricks. Is 2, 3, 180 what you do here. What you do here is you do minus 1 to the power of 3 squared minus 1 over 8, which is minus 1 to the power of 1, which is minus 1. Or if you prefer, you can write down root 2 cos 3 pi over 4, which is minus 1. Oh. There's just two different rules here. Or if you really prefer, you can say, well, no, 2 is not a quadratic residue mod 3, because mod 3 thinks square to 0 or 1, not 2. Right, okay, so the proof is going to use Gauss's lemma. It's going to do this counting for us. And, oh my goodness. It's going to do some really clever counting. Oh, this is going to be a nightmare, isn't it? Maybe this is my aim for today. Let's have a quick skim of what's going on. We have some stuff about those sets. I've forgotten what that is. It's now got a subscript P, so that's terrifying. Some unique integer C. I think this is like the positive negative idea. Number of B such that that thing, when you multiply by Q. So before we were thinking about 2P, now we're thinking about QP. When you multiply Q, does it go negative? Count the minus signs. Mumble, divide by thing to the whatever. We want to count, we'll know the parity of pairs such that, oh my goodness. Ugh. So B is in here, and this thing, when you take off C times P, you get a negative thing. You need some restrictions on C, right? No, maybe not. No, maybe not. Maybe this is either possible or impossible. So counting how many times this happens that you could subtract C. Is there a good idea coming? Oh, there's a diagram. There's a good idea coming. Mess around with the inequalities. Interested in pairs such that, wow. And then there's 4 regions of space. We're interested in QP is minus 1 to the power of A for the number of points in here. B is the number of lattice points in the box with that thing. So we're interested in minus 1 to the B. Aim, we want some weird mix thing. This statement, P minus 1 over 2, Q minus 1 over 2. We want P minus 1 over 2, Q minus 1 over 2, plus B minus A to be even. Okay, everything's in terms of minus 1 to the power now. I'll give them this. My cosines multiply in quite an awkward way. Powers of minus 1 multiply in quite a good way. Okay. So we want that plus B minus A to be even. So that's the number of lattice points in the box. Oh ho. The number P minus 1 over 2, Q minus 1 over 2 is relevant, having set up the box like this. This is ambitious. C in the top, D in the right. Okay. This is up to factors of even only if that is even. We can show that C equals D, then we're done. Here's a bijection. This is brilliant. This is not a proof of law of quadratic reciprocity that I've seen before. This is great. Find a bijection between points in C and points in D, like that. Quick check shows it's worked. That completes the proof. So this is just a sort of counting argument. Because Gauss's lemma gives us a counting way in. Okay, how am I going to understand this? I had a quick skim through. So I've got the idea that it's about counting points in this box. I'm going to try and draw some points on because, well, maybe I'll think first. I'm going to try and draw some points on. So I'm imagining this lattice of points. It's going to be that triangle C and D have the same area or same number of points in them. Okay. I think I want to understand these inequalities a little bit. I'm a bit worried about this B and C space. I thought C had to be quite a small number, but I suppose I was imagining multiply by 2. When you multiply by 2, you only have to subtract a little bit to get it back into that range, whereas we might have to subtract quite a lot. Right, okay, so strategy is I think I've got to understand these inequalities and then turn the page back. We also count, we'll know the parity of pairs of integer grid points. It really feels like C should be defined uniquely. Yes, unique integer C. Such that B is in that range between 0 and P over 2, strictly less than half P. P is odd. And when you subtract some multiple of P, you end up in the negative numbers. We've got this vague notion of positive and negative numbers mod P, which says the bit from 0 up to P over 2 is the positive numbers. And then the other bit's the negative numbers. And it feels a bit weird because it feels like positive numbers and then the negative numbers, but because of the repeat, because mod P arithmetic repeats, that's positive numbers on the right and they're kind of negative numbers on the left. You've got to split it somewhere, I suppose. And there's a proof of Gauss's lemma which says it doesn't really matter what you do, so long as you cover everything with the set you're calling positive and its negative image, as long as that covers everything. And oh gosh, something else about multiplying. The other proof was quite hard to follow. Okay. Pairs like this. So for each B, there should only be one of these, right? Okay, but this is a thin strip that I'm trying to imagine, which I should just look at the picture. From these inequalities, okay, here we go. So what is this? B is somewhere between 0 and P over 2. So this is the B axis. And C, there's some maths going on here. C turns out to be between 0 and Q over 2. Let's read it. So BQ minus CP being bigger than minus P over 2 means that CP is, oh gosh, less than this. Which is that C is less than this, divided by sides by P. Which says that C is less than half Q. Okay, that was fine, I think. And this is a restriction on C as well. This says that C has to be positive. Okay. You really do have to subtract some multiple of P in order to get down here, but not as much as half Q. Not as much as half Q, because you started, no, hang on, yeah, you started with a number that was only as large as half Q. B is as large as half. Trying to make sense of these lines of algebra. I guess I'll just leave them as algebra for now, but it's the intuition about how much you might need to subtract. Only as much as half Q. Times P is the thing you subtract. Half PQ, the thing you subtract. Because the biggest number is half P and you multiply it by Q. So you won't need to subtract more than that. That would be enough. Yeah, okay, it's about on how large these things go when you multiply them by B. Okay, good. I can imagine it like that, I think. B is on the large side. Here, B is on the small side. Whatever. Okay. I'm interested in pairs such as this. Now, let's try and test my theory. I think that these bands are quite narrow. Yeah, look, this band's really narrow. So this goes from 0 to 1/2. So the first grid point is all the way up here. This is a weird picture in a way. So that's 1/2. And in BC space, you can say things like when B is 0, C is minus 1, C is 1/2. So you get this kind of grid going on. And then, yeah, so this has got height 1/2. So I feel like, okay, there's the sets A and B that matter. They've either got a point in or not. I'm trying to count those. So I should try and draw this like, so sometimes these points are here in A, and sometimes they're down here in B, but they're kind of, there's never 2 points going on. I've drawn things below 1/2, which is wrong and it slightly annoys me, but never mind. Okay. Never two things vertically. Yeah, this gap's huge. CP minus BQ. No, what? Minus half Q? It's got the same gradient. What's going on? Q over 2. I'd like to imagine this as being a different line, different value. So instead of minus B over 2, when B is 0, C is some negative thing, minus PQ over 2. Maybe I'm wrong. Maybe this gradient. I thought the difference in heights here. The difference in heights is the difference in C values between the two lines. So I should take, for a fixed value of B, I'm trying to find like this height, I'm trying to just think geometrically about how this picture works. For this height B, for a fixed B, I should think about the difference in values of C on these two lines. Now, so if I do the difference there at the same value B, those would cancel, and I'll get the difference in my C values that I want, but multiplied by P. And it'll be, oh gosh, rather unpleasant. How should I believe this? I guess I'll believe it for now. Minus 1/2 P less than. B is large, less than 0. This thing. I wonder if this is supposed to be a 1/2 P. Yeah, let's scroll down. I'll be overreading this. No, they've written it here again with a Q. A is the number of lattice points. B, number of lattice points in the box with minus 1/2 Q. So this gives me the rather horrible answer that the height of this box is like, if I do that top line minus the bottom line, then the height of the box, the difference in the C values, it's like C2 minus C1 is what I want. Oh, so I should do this line minus that line or something. It's like, Q over T minus P over T, all divided by P for the height. It's height that I'm interested in, which gosh, I don't even know if that's the right way round. Oh, plus P over T, because I'm doing the difference. I want to do this one, subtract that one, which is a bit like more than one, it's one and a bit. Yeah, so I don't know what this link is here. And I'm going to count them. And then I kind of accept that the counting works out. There's some clever bijection to show that C plus D is even, leaving you with an even number of things in A plus B. Or is it A minus B you want or something? It doesn't matter if you're talking about even things. Those have the same parity. What's that got to do with anything then? So in some sense this is just switched P and Q, but it's kind of also switched B and C, which makes me very nervous. Switch the roles of P and Q. I think this might be beyond me. It's a bit much. Where on earth does that minus 1/2 Q come from? Can I see it above here? Can I see it up here? Minus 1/2 Q. Where's that come from? So my current understanding is that these are linked in that these problems are kind of the same, but with P and Q flipped. And then also someone cleverly has flipped the roles of B and C in the separate problem. So you have, like, on the one hand, this problem above here. Everything above here kind of relates to, or counting the things in the region A, relates to the problem for QB is Q a quadratic residue mod P? You're supposed to count the things in A. And you could do that again, but with a box of different dimensions the other way around, with Q over 2 and P over 2 this way round, and count the things up here. So the size of that box has got something to do with P over Q. Is P a quadratic residue mod Q? And then the clever thing someone has done is to put those two pictures together, because if you reflect this one, flip it down and stick it underneath, then you fill in the other half of the rectangle. And I'm trying to get my head around the fact that they've switched P and Q so that they're talking about the other problem, and they've switched B and C, that's the reflection. So this is the other residue, and that's because of the reflection. So this BQ becomes a CP, and this CP becomes a BQ, and then you identify that's that box over there. Okay, I no longer want to work out the height. I thought it was important, no longer sure. I think the height, and then this direction, I don't know what I think. Yeah, I sort of think for each B there's a unique value of C, right? So maybe that tells me it doesn't do this either, that this is also suspect. Maybe I ought to actually draw this. I'm not sure that I'm getting a good scale drawing. So maybe something that would be useful for me is to actually look at grid points for primes, I don't know, 11 and 13 or something. 17, make them slightly different. Actually, in the picture I've got, it looks a bit more like P is 17 and Q is 11. Okay, so then I'll be trying to draw the lines, just visualizing this box. I'll be going up to P over 2, be going up to Q over 2. Yeah, this seems doable. Seems like a Desmos moment, right? Yeah, because these would be fine, wouldn't they? These would be like 11x minus 17y is equal to minus 17 over 2. I'm just having trouble visualizing what that line looks like. And luckily, we have Desmos for things like that. Okay. Okay, we're going to switch backwards and forwards. But what do I want? So I want a grid of points. That's surprisingly hard to do in Desmos, isn't it? Desmos let me do a grid of points if I do. I've tried different things over time for doing my grid of points. I have some stupid hacks, but let's try simple things. So what do I want? I want points like this, 1 up to. Thank you. I should save my work. I am logged in. Look, that's nice. QR. 1 up to 17. 0. Oh, it's already not happy with me. It's too many dots. 1 up to 17, but I guess I want 17 over 2. Good, okay. 1 hour of Desmos is problematic. Ah, do I want 0 in here? I think I do. Don't want, yeah, we lost an hour, right? It was pretty bad. What I kind of want is just to tell Desmos that I want 1, 2, 3 over here, but it plots them like a graph. So I kind of want this thing A for like some list L, where I set the list separately, but I don't think it likes that yet. Just puts it in and does the list comprehension like that. So I think I'm going to do a stupid hack, which is just to show the grid points. Maybe showing the grid points is not the important bit. Maybe I should focus on things like the box itself. I think if we did a wide, we'll go for a wide box. Grid points. We want to, a positive viral Twitch clip. Only good Twitch clips. I'm pleased with my choice of 11 and 17, right? That looks just like this box. So quick look, just like that one that I've scribbled all over. Let's quickly change some settings to make this pretty. Okay, we're trying to count the points inside some regions of this box. And I think the lines we're interested in are like this. See if I can remember them. The other one involves switching the roles of X and Y and 17 and 11. So you end up with this, like that. Okay, this is already helpful. Let's put that as blue as well. I seem to go for blue for everything. So I can kind of test my ideas about whether there's multiple points horizontally. It looks like I was wrong about a bunch of things. Or is there another line down the middle? There is a line down the middle, the BQ minus CP equals 0. Which for me is, I should write out something like 11x minus 17y equals 0 for that line down the middle. Now, if I was clever, I would have set this up to be something like p equals 17, q equals 11, so that we could now go in and change those things. In case we change our minds? Oh, what are we thinking? I think that's worth it. How bad can it be, right? You know, just go in and just change everything. 11 is Q. So it's quite nice actually. You can just watch, see if anything breaks on the right hand side. 17 is P at the moment. I think I've got all the 17s and 11s. Good, okay, I've got some lines. This is going to be a little bit of a pain, but I'm going to try and mark the grid points, these things that we're counting, for oddness and evenness reasons. I'm surprised these triangles are not the same size. I'm surprised they're going to turn out to have the same number of grid points. They're really not the same size. Same number of grid points? No, their sum is going to be even. Right? Drawing the picture helps. Size of C and D equal. That's crazy. Crazy. Right, okay. So Desmos, not great at plotting a grid. I've achieved this before by having like a long list and then plotting like using modular arithmetic. So like this. So I have long list, 1 up to 100. This is something I've done before. So then you can do like mod. Oh goodness me, what am I doing? X is mod L 10. That's how Desmos does modular arithmetic. And Y is like L minus X. Well, no, I shouldn't have used X and Y. Then I've got, so then if I plot X and Y, and if I've done it right, then I get a grid of points. No, I don't. What have I done wrong? Y is a 100 element list. X goes sensibly up to 9, back down to 0. And this is this. Oh, am I supposed to divide this by 10 or something? There they are. Good, okay, so I can make grids like that. But I want to do something slightly funny here. I don't want to mod 10. I want to mod that P over 2. Look at the picture, look at the notes. That was P over 2. And now we're going to get into trouble because now my grid's not square. How am I going to get around this? With difficulty. So you've got integers up to P over 2. Oh, I should take my integer grid and multiply it? No, I shouldn't. I want to stop at P over 2. Well, this is awkward. Can we do something like, I just want to plot grid points, right? Suggestions in chat are welcome. So points x, y such that x is less than P over 2. I can't even do those. Can't even do those. I know how to do a square grid where it stops at some integer. Stopping at half integer is a bit annoying. Oh, it is half an integer. P's prime, but it's half an integer. Can I do something with that? Because every other row is shifted by half. Let's bring it back. every other row was shifted by half. So my problem was that this, my problem is that that is out by a half for some of them. So I should use even numbers and mod it with even numbers and mod it with P. Every other point was happy. No, this is nonsense. I think this is just nonsense. No longer sure what I'm doing. Good, okay, what am I doing? I've just brought the evens, but they're still shifted by half at the wrong points. We're going to get around this. So my odd rows are shifted by half. So what if I want to skip half of them? This is doable. And by the way, I could probably scale that nicely to be equilateral triangles. They're not equilateral triangles at the moment, but you can play with it, right? It looks a little bit equilateral. There we go. If I ever need an equilateral triangular grid, I know where to look. Mod half. What do I want to do with this? Well, so maybe I just want to. Oh, these ones are over at 0 as well. I should start at 0 on my list. Put that one as well. So I'm going to subtract 1/2 if y is, so y is going, y is supposed to be going 0, 1. It's not even doing that right. Why is it not even doing that right? 9. It's mod p over 2, right? It's subtracted. What's it subtracted? Well, it's got up to it's got up to 8.5, and then it's looking at the next number, which is 9. It's done that mod 8.5. This is now an hour of me drawing a square grid and then doing a little bit of counting. 8.5. So it's looks the next bit more than 8.5. So that's a half, which is why it's got a half, one along a half. There's also subtracted 1/2, and it should be dividing it by p over 2, I guess. Okay, not 10, but p over 2. There we go. That's okay. So I was looking at the difference between 8.5 and 10. Very annoying. So all I want to do is, if y is odd, then subtract if y is odd, then subtract 1/2. Not from y though, from x. Bing! There, it's gone left, and it's rolling over at the wrong point. It's slightly missing half of these over here. One mistake, different mistake comes back. I didn't spot that. So it's shifting left because of a tiny amount of. That's not rounding error, is it? It's just how long it takes. I want it to draw another point at p over 2, even though mod could fudge it. We could add a half instead, and then the problem's all down the left hand side where you can't really see it. Yeah, I might just do that. That seems better. Well, just inside, look. Let's just fudge it. I'll draw those ones in separately. This is so half a job. That's not even happy with me. So too many dots again. Too many commas. There we go. If it's worth doing properly, it's worth doing properly. I don't want 100 of these things. I want PQ over 4. I used to be on Twitter as biggest triangle. Hi, Charmander. So I used to be a geometrical shape. I was the biggest triangle on Twitter, but no longer on Twitter. So if you want to be the biggest triangle on Twitter, then that spot's currently up for grabs. I'm having trouble working out how many points there are. Oh no, it's a pickup line. I don't get it. Yeah, there we go. It's getting better. Keep going. What a great troll. Or, I don't know, is it a troll if they're nice? Cool, right, I've got bored of trying to get the right number of points in this grid, so I'm just fudging it. It's very, very bad. Because now if I adjust it, I haven't quite captured the right thing. I'm going to try a little bit harder at this and then give up. That's my strategy in life. What do I want here? That's P over 2. How many are there? P minus 1 over 2. But plus 1. Plus 1 over 2. Okay, so it's this, right? It's got to be this. Oh, that's way too many. Why is that way too many? I'm just trying to multiply numbers together now, right? P over 2. 1, 2, 3. P minus 1 over 2 is 8. But then add 1. So you get P plus 1 over 2. Then multiply. Subtract 1. I've still got the plus 3. It's still too large. This is mad. I'm now just counting the dots. Oh, I put in those extra dots. It's now just fudge over fudge. I'm so unhappy with this. I think Charmander might actually be a robot. It might be a robot. But they did a maths one. Oh, it's very hard to say. It's very hard to say. I'm going to be forever bugged by extra points that are just outside of range, aren't I? That's just my life now. What if I just draw all integer points? Would that be fun? Would that be fun? If I stop trying to get exactly the right number? Yeah, let's just go for all of them. Yeah, forget this. This is really horrible. Let's go for like max PQ. Let's go huge. Squared. And actually times 4. Some huge thing. Let's go like grid width. Max is n is like the maximum of PQ. Let's go for n squared. Like double n squared. So show the list and just mod it with respect to n. Divide by n over here, take that off. Don't do any weird shifting. Just do that like that. Take off one factor of n here. Take off another factor of n here, but I've changed my mind about the modding. Just plot those, please. There you go, loads of points. Don't do any weird stuff. Just show me all the grid points in the world. Oh, can you restrict? Oh, we did this before, didn't we? Oh, you can restrict. This is much better. Oh, it's on an ore. It's on an ore. That's not what I expected at all. But that was briefly good. Okay, not quite that. More like that. Let's keep the less than or equal to in here. P's not going to be number 2. That was the lone one is a little bit more economics. They're up by a half because I shifted down by n. I should shift by There's some amount of dodge, and I respect that a little bit, I suppose. Can I put a second bracket on here? No. Can I go L2? And don't plot it, but show me L2. No, okay, never mind. I've restricted it a bit. It really feels like I should be able to go naught less than y less than 2. Why is it doing that? Why is it doing that? It's doing an or. It should be doing this. It should be doing and. No. Okay, never mind. That's hilarious to me somehow. Good. Oh no, I'm annoyed. I'm going to get rid of that. Okay, we've got a grid of lattice grid of points. Let's turn off the Desmos grid and just look at this lattice. Ah, oh, lovely. Right, okay. So now we've got this really interesting pattern down the middle where, yeah, as suspected, the height, there's never more than one inside this region for any particular height. And the same thing's kind of true on the width this way. Also looks to be true over there. Let's put in some of our favourite prime numbers and look at how they have the same property of not having many dots in here at all. And the claim is that... Ooh, that was just inside. The claim is that this triangle down here has got the same number of dots as this triangle up there, which doesn't look very true, but you know, I'm not certain if the edges count or not. I think they don't. So try and keep that in mind, I guess. I think the edges don't count. So then I'm looking at here. What's this? 5 and 1, 2, 3, 4, 5, 6, 7. And this side goes 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5. But then the triangle's weird. It goes 2 steps, 1 step, 1 step, 2 steps. Maybe 2 steps, 1 step, 1 step, 2 steps. The middle bit's kind of so narrow that maybe that's what's going on. The middle bit's so narrow that you get this kind of... Is that one? Where's this one paired up with? That one is outside the region. So the claim is that these big triangles have got the same number of points in, which I still find very surprising. Sorry, but I do. Oh, that one and that one. Okay, so there is some sort of... It's not quite rotational symmetry because these lines are parallel but not equally separated. I'm sort of surprised that one's outside and that one's outside. Maybe that's not how it works at all, but... Bold guess. 1, 2, 3. 1, 2, 3. Quick check. So 13 and 19. 13 is 1 mod 4. 19 is 3 mod 4. So this should be the case where, oh gosh, are they equal? P over Q and Q over P are equal, and so there should be the same parity of dots. 1, 2, 3, and 1, 2, 3. Origin probably doesn't count. Same number of dots. That's nice. Let's try primes that are very different. It's going to be a little bit harder to count these. 1, 2, 3, 4, 5, 6. This one's got outside the line only 1, 2. Those are equal. I picked again 2 things. They're not both 3 mod 4, are they? So let's try picking something that is 3 mod 4 over here, like the primes that are 3 mod 4 and quite large. Primes that are 3 mod 4. I can't think of any multiples of 4. 43. There's a good one. So they should have a different parity of dots in the gaps. And this gap is now so narrow that it's hardly got any dots. 1, 2. Is that inside? 3, 4. Whereas this one's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, those are the same. 1, 2, inside. 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. The same. Those are both 3 mod 4, right? Oh, 13 is not 3 mod 4. 13 is not 3 mod 4. Is it? No, it's not. It's 3 more than 10. 10 is not a multiple of 4. It's all fun and games. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 upstairs. And in the smaller bit channel down here, 1, 2, 3, 4 dots. Different parities. Different P over Q, quadratic residue, Legendre symbols. Right, gosh, okay. This feels very difficult. Does not feel like the sort of thing where it's not the case that you look at the picture and it's like, oh yeah, obviously those triangles match up. Let's watch and learn. What time? Oh, is it almost 4 o'clock? Almost there. I've got 5 minutes. You want a cup of tea? Oh, this is cold. So, number of lattice points, which I did briefly have to think about in the box. Looking at strict inequalities, not including the origin or things on the lines. Probably there's nothing on the lines because of things being small and P and Q being coprime. Feels likely. The line's got irrational gradient, right? No, the line's got gradient P over Q or something, which is in lowest terms already. So apparently we're trying to count these things. I kind of believe that there's not very many points inside there. It's not this many, for example. We want this plus B minus A to be even, and it comes down to counting B plus A. Yep, okay, there's just factors of like taking off 2B, but that's the same parity, so it's all okay. It's like the difference between the two of them. You've kind of got these two different diagrams, and we've glued them together, but maybe we'll think about the difference. If we can show that C equals D, then we're done. Here's the bijection. B goes to 1/2 P plus 1 minus B. That's a reflection. C goes to that, and that's also a reflection. So this is just a rotation, right? It's a pair of reflections in the midlines, right? Yeah, okay. So there's rotation about the point, P plus 1 over 2, Q plus 1 over 2. Let's plot that point in decimals. Q plus 1 over 2, Q plus 1 over 2. Oh, come on, put all of it upstairs, please. Q plus 1 over 2. Where's that gone? Oh, it's also in black, so I can't see it. The middle? Oh, I've done something stupid. It's up there. Why is it up there? Is this like mod P or something? What's going on? P plus 1 over 2 minus B. Oh, reflection in the line, that over 2, so over 4 for the point of... reflection in the line means halfway along. That's suspiciously not quite on that line, but we'll ignore that for now. The idea is you reflect twice. You take these points and find the one that's opposite. I'm going to need a little BC thing with sliders, I think, so that I can test this out. I'm being a bit of an idiot about translations, but it's 4 o'clock on a Sunday. We're doing our best. So try and visualize this, right? Because now I can grab the red point, my BC point, whoop, I can hold it over here, and I can see the effect of these rotations is to put a point. The effect of this transformation is to get the purple point over there. Oh, I love Desmos. So as I count along here, you'll get the same number in this row. And then I sort of understand. Yeah. And then I'm a bit worried about this one, right? because the line's not in the same place. It's in almost the same place, but the line's not. So there's something to check there. I'm going down here. That's all right. That's all right. And then this one is just inside, and it still surprises me that it's just inside both lines. Ah, you've redeemed tea time. I don't know how to handle that at exactly 4 o'clock, which is the time I normally stop. I think the most fair thing for me to do, since you've redeemed channel points, is for me to stream a little bit more. So I'm going to make a cup of tea and let you think about points inside a rectangle. Am I going to check this? I've never understood the law of quadratic reciprocity. Cool, right, okay. Let's make a cup of tea, come back, have a look at this. I think I'll leave this. Oh no, I'm going to go be right back, but I'll spare you the ad break. Back in a minute with a cup of tea to try one last bit of understanding. See you in a second. Thanks, Mary. How much have we understood today out of 10? It's not been a great stream for understanding. I'm at 3 or 4. But I saw your 2.5. That biased me a bit. This crashed. It's all going wrong now, isn't it? Oh no, there we go. It was about to crash, but we saved it. 4, I think. We saw some nice quadratic reciprocity. We saw some nice Legendre symbols, messing around with them. I think we can save it by kind of giving up on checking this. I do not believe it's a quick check. I'm suspicious of this, like really suspicious. But what are you going to do? I think we save it by understanding what this is for, which I think might give me more context on what we're trying to achieve. So, sponsored by Mary Atene in chat, who asked me to go and make a cup of tea, redeeming channel points. We're going to keep going until we understand something. Exercise. Oh, I don't want to do an exercise right now. If they're the same mod 4A. What? No, we're not doing this. Yeah, well, use might be pushing it. But the idea of quadratic reciprocity helping us to do some tricks, that kind of thing that felt vaguely like an algorithm halfway through. I think that's going somewhere. I'm terrified though because I've turned the page and it's introduced a new sort of symbol. I suppose you're going to tell us about mod 10, is it? Composite moduli. G'day. Generalize it. Keep this multiplicativity. So let's try and keep that. Okay, what's going on here? Mod 4A. Then, ooh. It's very tempting, right? What if P is Q plus 4AK? IP, maybe I'm not up for this right now. Maybe I'm not up for this. Maybe use this directly and use it to prove LQR. That's not. Mod 4A, it's so weird. Anyway, okay. Let's say n is a products and primes without any squaring or anything. So 10. Then this thing, where API, and this is the Jacobi symbol because, oh no, not 10. N has to be an odd number. Oh, not necessarily distinct. I'm really not reading this well. Bad day for understanding. Bad day for reading. Reading comprehension. And be an odd number. Slightly more efficient would be good. So I think the thing about prime factors of n squared plus 1 is quite interesting. I'm hoping that we get around to doing more of that. There was a kind of bit in the lecture notes before reciprocity, my bugbear, the thing I may never understand. Before that, there was a bit about when you're just using Fermat's Little theorem to count how many quadratic residues there are. And then that's got something to do with prime factors of n squared plus 1. Open problem, I think. How many times is n squared plus 1 actually prime? So I kind of want to know more about this because I think it relates to more prime number stuff. And I agree that's number theory for the sake of doing more number theory, but it's maths, isn't it? It's all terribly useful for factorising numbers, presumably. Okay. Empty products. So we're going to define it. Give me all your primes and just multiply these things together. So it's going to be 1 or minus 1. And then it would be nice if that had something to do with quadratic residues, wouldn't it? The Jacobi symbol is the Legendre symbol if n is prime. For 15 here, like this. No, odd numbers only. Let's circle that. Odd numbers only. Okay, hello. 2, 3, 2, 5. Okay, 1, 3, 15. 3, 3, 0 because those are equal. 3, 5. They're not. Sorry, they're not because they're equal, but because they're not coprime. Remark, brackets really important. It's possible to have 1 even if A is not a quadratic modulo n. Okay, so what's the point? Okay, so why would we do this? Oh dear. Oh dear. If it's true that It is true. It is true that if an is minus 1, then A is a quadratic non-residue modulo n. Okay. You don't want to talk about cryptography too much, do you? Jacobi symbol is multiplicative in two senses. Whoa. If n is an odd number and a, b, and integers, then upstairs, because of the normal stuff, split it into primes, do each prime separately. That was the Legendre symbol, that one was good. If I went in an odd natural numbers and a is an integer, then this thing by prime factorization or something. Good. What else am I? This is the thing I care about, except only for odd numbers. For odd n. Do we know that? Have we proved that it's okay? So we've got some link with quadratic residues mod n again. But first, let's calculate. Minus 1 n is minus 1 to the n minus 1 over 2. This looks Fermati. 2 and odd natural numbers. Is it just going to multiply up? These look like the things we had for odd primes, right? Minus 1 is a quadratic residue mod p if minus 1 to the p minus 1 over 2 is 1, the symbol. Okay. Say n factorizes. Hello, my memories TV. How are you doing? Can be like. I'm easily distracted. I'm trying to learn this, but if I don't help them, maybe someone else in chat might help. Last time we did this, the master gave us really hard maths. What have you got? Oh gosh, congruences to 3 mod 4. It's not a snack. Nah. Nah, I looked it up. There's a screen sharey sort of thing. I'm not into this. Currently streaming, dude. Oh, imagine that. Once this is finished, I'm going to go and do something totally different. So I'm not. I ain't clicking that. Chat's going to bet. Okay, hi. I think you're probably honest. Just my gut reaction, but first time chat 3 minutes ago. Here's a link to a thing. What was I thinking of? What's the little dumpling? They switched the vowels. It's a little dumpling. That's what I was thinking of. You got to do calc AB. That's differentiation and stuff. Should be possible. Calc AB sounds like stuff that I know how to do. Just I'm going to click on a dumpling link. Right, I'm going to carry on reading this. Oh, you got to integrate something. What do you have to do the antiderivative for? I'm going to get distracted. This is fine. Solving the antiderivative. Yeah. Okay, you got a graph. Whee. The value of big H of 9. Okay. I don't know what H is. Oh, and H of 12. It's going well so far. It's a giraffe. You know how tall the giraffe's neck is. To find an area. This is going to be the area under the curve. Oh, area of the graph. Oh, I wonder if big H. So, okay. What's h? I've labelled it on my graph as if it's the height of the giraffe. But you could. So we don't know what h is. Can you tell us anything about what h is? So okay, you've got like h9. You know the value of h12, and there's a graph somewhere. But like, what area are you trying to find? What's h got to do with anything? What's this? What's this graph? Okay. I kind of trust Chit's each portion of the h is part of a line. No. What? No. Oh, h. You mean a piecewise function, right? You mean a piecewise function? Yeah, I'm getting there. It's not a giraffe, is it? It's part of lines and graphs of circles. This seems like quite a Calc PC thing to do, right? Something like this? I'm still not going to click on the dumpling. You got a bunch of lines and circles. No, maybe not. I don't know what you've got. Oh, you do have something like that. You're trying to find the area under that. It's something like this, right? You can find the area. So if it's piecewise, this is Discord moment. Oh, I'm not getting Discord. Chat's in on it. Chat's engaged. Yeah, okay. You're just gonna split it into bits, right? You're gonna chop it up into little bits. You've told me it's part of lines or circles, so you split it into little bits. I told them not to. Oh, okay, I was going to describe. Okay. Oh, is it defined geometrically? Am I okay? So I'm putting you on the spot to tell me what h of x is, but maybe that's the question. Like you've got some drawing of an antelope or something, and you want to convert it into lines. Herb saying describe it. Gosh. Against my better judgment. Pop. Okay, good. So you've got to find the area. My strategies for this at Calc AB is something like split it into different sections with bits with circular arcs and bits which are. Hello, Oatmeal 365. I kind of agree, right? Also high, but this is somehow. What I like. I like to imagine that Oatmeal has like furiously made an account and be like. You've got to find big H of 12. We've all been there. Possibly, this is really fun trying to piece together the question from what people put in chat. I'm having a great time. Possibly there's a small h for the function and a large h for the antiderivative. Am I getting close? Is this like there's some picture of small h and people are trying to integrate it to find capital H or big H of 12 for the antiderivative, which is possibly going to mean something like integrating small h from 9 to 12 to be big H of 12 minus big H of 9 is possibly the thing we're missing. Right, you can only see lowercase little h of x. You've got some shape. And possibly you're given an equation for it, or possibly you're going to have to work out that it's like, oh, it's 2 plus 3x over here, or maybe it's square root 1 minus x squared for a little bit of something else. So I think key thing from my... And then people in chat going to do the numbers. Oh, herb. Oh my goodness. I almost got it. Straight line segment of gradient 5/4 between 0 and 5. Between 5 and 9. 5 and 9, it's a quarter circus of radius 5. Ooh, radius 5 is interesting. Because it only got as high as 4, right? I reckon maybe it's a quarter circle of radius 4. I feel like... radius 5 will be interesting because then it would go negative. 4, 0. I think it's got radius 4. Oh no, radius... gradient 5/4 in the first bit. This is great. This is brilliant. Then there's a quarter circle, and then a straight line for gradients. Oh my goodness. Constant at -2. Oh wow. It goes up to 5. It definitely goes up to 5. This is brilliant. Okay. H of 9 is 1. Oh, so maybe there's some things you don't know in the question. No one's really told me yet. Max is right, maximum is at 4, 5. And then so it comes down to 1. And then there's a straight line of gradient -1 to get down to from 9 to 12. And then up to 14, I think probably doesn't matter because we've just been talking about H9 and H12 in chat. Right, so this makes me think that this is just daft, right? 11 to 12 -2, the constant bit. Oh, 11. to 9 to 11. I'm so upset. Oh dear. I'm out by 1s and 2s. I'm losing interest, chat. Okay, here's my theory about what the question might be. I'm still refusing to look at the question because I don't click on links. But my theory about the question is that there's some picture of h which is hard to describe. And maybe there's some things you know about little h, some things you don't know about the function of little h. But the question is asking you for something quite straightforward, which is the difference between big H of 12 and big H of 9. I think maybe you're told big H of 9. Somebody said this at some point. You're told big H of 9. I think maybe work out... I can maybe work out big H9 minus big H0. It's very tempting to take the description that Herb gave and try integrating it. But we don't need to. We should just do the integral from 9 up to 12, right? We should just look at the integral from 9 up to 12, which I think is after the quarter circle stuff has happened. After the quarter circle stuff has happened. So that'll be nice that we won't have to think about quarter circles. Oh, Calc AB. Don't know how to integrate. Well, you know the area of a circle. You'll be all right. But we don't have to, right? Because whenever you're integrating a function with definite limits, if you've got an antiderivative, so here capital H, I reckon that's the name for your antiderivative, but nobody's explicitly told me that in chat yet. That would just be the difference. So I think we should take whatever the bit of function is between 9 and 12, which I think from the script is probably straight line bits. Just integrate that bit. Can't be that bad, right? Straight lines. And then that'll be the difference. So what is it? Something like 9 up to about 11 of... I don't know what the equation of the line is over there. I can probably work it out. It had gradient -1 and it started at gradient -1 and it started I think at 9,1 people said maybe. So that's 10 minus x or something. Don't really know, haven't seen it. It's like integral to the 12, 112. Oh, yeah. Cool. The thing you've said, integral 1 to 12 hx dx. I would guess that that's big H of 12 minus big H of 1. But also, this thing on the left is impossibly difficult to work out. People are struggling to describe it in chat. It involves circles and lines. Horrible. I say don't work out that. Because who cares about big H of 1? Don't do that integral. Do this one instead. Because that relates together big H of 12, the thing you want, I think. Big H of 9. I think. It's possible I've misunderstood entirely. Right, that was great fun. Calc AB, but I can't see the question. I think it's a good handicap, I think. What are we doing there? 10 minus x. Can't confirm your number. Mountain Ash is asking chat whether it's maybe the number 5. Maybe like they're going to integrate some straight lines. I'm going to let my memories integrate some straight lines. Erb's got maybe 5 as well. I'm trying to remember what Herb told me about this bit of the graph. So I think it was from 9, 1 coordinates down to, I think, 11 minus 1. Do the segment again next week. This segment is this bit of the show, right? Where it's the telephone game. The telephone game, but also Calc AB. Did we help? My memories. People come by quite often. We have never helped anyone successfully. We just hang out here trying to learn stuff, and occasionally someone will yes, they got 5 as well. Chat. We may have helped someone with their homework. Congratulations, you are the first person ever to benefit from 11 minus 2. There you go. First person ever to benefit from this stream existing. 12 minus 2 to 14, 0. Oh, it comes back up again afterwards. Rubbish. We don't care. We only want this bit. Lovely stuff. Right, good. Okay. Do this rectangle, right? What have I got? A rectangle of 2 by 1. So 2 by negative 1. So minus 2. Sort of triangle. Good. We don't know maths. It's just what we're like. Yeah, a bit worried about negative area, which, you know. I'd probably do this with negative, like, what's that, 3, 2, if I use these numbers, 3, 2, and a couple more over here. Or maybe only one more over here. Yeah. 11 minus 2. Yeah, 3, 2, over 2, so this bit's got area 3. But then this bit's got area, what is that, 1 by... where is my rectangle? It's down here, 0. But then add on an extra 3 for the width. Wow. I'm not quite right, but I'm close. Is 9, 0 not 9, 1? Ah, solved. We solved it. Great, cool. Telephone game. You tell me the coordinates, I find the triangle. Ugh, I don't know. What do I like? Can we remix this for Matt? So remix this for Matt. There's a big quarter circle in there that people were a bit worried about. But it happens before 9. So remix for Matt. Please go and actually calculate h of x. Given that h of 9 is whatever it is. It doesn't really matter. You get to choose your number when you set up your antiderivative, if lowercase h is the real thing. You get to choose the constant in your antiderivative. It's all the same as all to make constants, but you can use any constant you like, and that's also an antiderivative, and it represents integrating from different start points, which is the key idea in this question, I think, is the idea that you can integrate from different starting points to avoid horrible quarter circle areas. Matt remix. Yeah, give me h of x. It's not very nice. We do this every week. We need my Memories TV to come back and give us more Calc AB questions that I can't see. Oh dear, what are we calling this? It's not chill, is it? What are we doing this? Calc AB telephone game. Don't feel bad. Part of the challenge is maybe it's good if I'm putting my spin on it. But being able to explain what you're trying to do is sometimes the hard bit. It's also why asking for help. Blind maths. Maybe cool maths instead of chill. My memories TV before you go, there's a running joke on this screen that I think that 39 is a prime number. I keep getting it wrong. Sometimes for the meme, and sometimes because I genuinely forget that 39 is not a prime number. I'm trying to learn number theory. Right. Right, good. Okay, that was great. This section was sponsored by Murray. Yeah, it looks bad. It's not that bad, really. It's got a lot of acronyms in it now. Use the definition of the Jacobi symbol, which is like what you did with the definition of the antiderivative was important for you. The kind of ideas or the proof strategies. Some similarities. How much do I care about this? So I suppose I don't mind. I'm going to skip ahead a tiny bit. Because what's the point of this Jacobi symbol if it's not telling me about quadratic residues? I mean, there was a throwaway comment that says maybe it's... Do not use factors as primes. We're doing more calculations over here. Okay, good. And then it just changes to be binary quadratic forms. Maybe the Jacobi symbols come up and they're relevant later. Oh, I know. I've heard this Grothendieck joke about 57 being prime. What's the punchline is something like you can't both be right. Thanks for the follow. We're live at 2 o'clock. We're live 2 o'clock till about 4 o'clock each Sunday. And very occasionally we're helpful. Thank you, Memories. You weren't here for the bit where I admitted my hearing loss due to being in my 30s. Good, right, okay. I haven't understood what these are for, but I kind of believe that using composite numbers and just multiplying together all your primes downstairs is something that you could do. So I'm skipping all the proofs for Jacobi forms, and I will be looking, I think next time, some binary quadratic forms, which I actually do care about quite a lot. Look, primes of the form. We're going to start finding rational points on the unit circle and stuff like that. Solving Pythagoras's, finding Pythagorean triples, I think. That sort of thing. Maybe. Ellipses, integer points, numbers. Right, good, okay. Take care, everyone. I will see you next week for more chilling around trying to understand number theory. Maybe one day I'll come back to my bugbear of law of quadratic reciprocity. Have a lovely Sunday afternoon. Bye. Ooh, thank you for the follow. Who was that? That was Oatmeal. Thank you for the follow, Oatmeal365. Bye.